Good evening and a very warm welcome to all our viewers, subscribers, and passionate members of Physics for Students. Today's episode is a very special one. We bring you a profound journey through some of the most fascinating ideas in theoretical physics. The podcast is titled From General Relativity to Quantum Fields, and we are thrilled to have with us today distinguished guest Dr. Ashmita Das. Well, Dr. Das is a theoretical physicist and currently serves as assistant professor in the Department of Physics at SRM University, Andhra Pradesh. She earned her PhD from IACS, the famous Indian Association for the Cultivation of Science, Calcutta, where she worked on extra-dimensional theories with deep implications in both particle and gravitational physics. Her academic path includes prestigious postdoctoral research at IIT Guwahati, IIT Madras, and the SN Bose National Center for Basic Sciences, where her focus evolved towards semi-classical gravity, the Unruh pulling effect, and the intriguing interface between quantum theory and curved space-time. Currently, she explores the frontiers of relativistic quantum information, quantum entanglement, Unruh detectors, and particle production in the curved spacetime, all while probing the mysteries of dark matter and modified gravity. In today's conversation, we will trace a conceptual arc from Einstein's elegant geometry of spacetime to the strange and wonderful world of quantum fields, black hole thermodynamics, Hawking radiation, Unruh effect, and few other more. So whether you are a researcher or a student or just a curious mind, this episode promises insight, depth, and inspiration. So thank you all for being here, and don't forget to subscribe to my channel Physics for Students, and a very, very warm and a heartfelt thanks and a welcome to Dr. Ashmita Das. Dr. Ashmita, a very warm welcome to this podcast.
Thank you so much, Shona, for inviting me. I'm very much feeling honored that you invited me in this platform. Thank you so much and exposed me to this wonderful audience.
Absolutely. First of all, one of my very own subscriber, he is doing his studies from United Kingdom, London, Fabio Mongilo. Hi, Fabio. This is Shaunak, and Dr. Ashmita, this is Fabio, a very old
Hi, Fabio.
subscriber and has been supporting us for a long time. Okay, Siddheshwar Mukhopadhyay, he is telling hi, ma'am.
Hi, hello, Siddheshwar. Nice to get you guys over here. Great.
Okay, so let me set the goal and how we will be doing this podcast. Now, Professor has prepared an amazing presentation, and she has handwritten all those equations which she will be producing and lecturing throughout. Requesting all the subscribers also that if you have any kind of a question in between, which is related to the flow of the program in physics, please let us know through the chat box. Professor will take the question, and again she will go ahead till the end of the presentation. Okay, Ansh Patel is telling thank you, sir, and welcome, Ashmita. Thank you, ma'am. I think you know these people, possibly.
Yeah, maybe.
Okay,
Yes, I
just
know. Yeah.
yeah. So a quick note from Saurabh Bhattacharya. Hi. So hi, Saurabh. Samita Basu also telling hi. Samita Basu, yeah. Hi, and Anjana Krishnan, hello. So we are done with the hi part, and now we will start with the presentation. Professor, I am going ahead from the first part, and you can start and go ahead. As I have told, let the subscribers have any question. You can stop in between, and we can go ahead with that.
Thank you, Shona. Two things I just want to mention briefly that feel free to stop me at any point. Do not hesitate, please. And number two, feel free to call me Ashmita, write Ashmita by my name, no issues in that. So, basically, Shonok told me that if I can make my presentation or my talk like general but yet technical, lesser technical, so that I can at least convey my purpose of being here or the purpose of, let's say, doing my research for quite a long time. So I have prepared a mixture of these two. Like somewhere I have developed the concept intuitively, somewhere I have introduced the very required mathematical steps. So that is why maybe some of you, if you find it technical, please feel free to stop me. I'll try my level best to explain those in detail to you physically as far as I can. So I gave the name very general, that discussing GR and semi-classical aspects of gravity, especially in the context of black hole spacetime. So let us go to the next page. So it is, we all understand, say, Newtonian general relativity or Coulomb uh, electrostatics, the laws of electrostatics. These all were very much successful in their domain, and we were very much comfortable with this kind of concept. But what happened is that gradually, our tendency is always to complicate our life by asking so many questions. And that is what exactly happened when Newton proposed general relativity and Coulomb proposed electrostatic. So all these things were progressing at their pace, and it was really a big success. But people started asking that what is basically causing this impact. That means, suppose, let's say you have a E minus and a E plus charge. So the moment you move the E minus charge a little bit, the E plus, it reacts instantaneously according to the Coulomb law. In same thing you can visualize for the gravity. Suppose you have two masses, m1 and m2. If you move m1 little bit, m2 will respond quickly to the gravitational attraction. So now people were asking that who is communicating, or what is basically this intermediate communication, that how these two things is happening just like this. So it is called action at a distance, and it become instantaneously, I mean, affecting each other. So now when Einstein's special relativity came in the picture, people got very much reserved, because they were trying to ask that, as Einstein postulated that no signal can move faster than the speed of light, then how this instantaneous cause and effect things is happening in the framework of Newton and Coulomb, etc. So now the point is, then Maxwell felt the urge of introducing the field theoretic concept in the electrostatic and magnetism, and he punched it as electromagnetism. So why he earned the field concept? Because field is a very local concept. A field phi, it depends on t, x, y, z, all the parameters, and field concept is compatible with the relativistic effect. Exactly, Maxwell have shown that the speed of the electromagnetic wave is absolutely the speed of light in vacuum. So basically, it was the Maxwell electromagnetic theory was compatible with the special relativity, and this action at a distance you can justify if you say that a field basically is propagating and making this cause and effect things. But absolutely, this is not instantaneous. It should follow and should be consistent with the special relativity. Similar thing Einstein earned, and Einstein basically implemented in the formulation of general relativity. He actually designed uh, the gravitational force as, I'll come to the curvature later, but initially I'm saying it as a gravitational field. Now, one step further,
Doctor,
Einstein,
we have a question. Can we take it if you allow? Okay,
yeah, I'm not able to, yeah.
Jason is asking, if the dominant body is in a gravity well, why doesn't the orbiting body creates its own gravity well instead of being in the perimeter of the first?
Yes, of course. So I'm just coming to the point, Jason. Just hold for a few seconds. So
Yeah.
when Einstein formulated the general relativity, it was telling us that, let's say we have a massive object. That massive object, according to the picture, as you can see on my slide, that it actually curves the entire space-time around it in such a way that a lesser massive object will actually follow spontaneously. It is basically, this white ball is basically spontaneously following that path due to the curvature of the space-time. So basically, in your question, if you have a massive object, it can work the space-time around it in such a way that the lesser massive object will follow the geodesic. I'm coming to the point of geodesic. Geodesic means the path spontaneously chosen by the particle which is freely falling under a gravitational field of another particle. Only the gravitational field. Here, no other forces are applied at that time when I'm defining geodesic. So basically, in your question, it is basically rooted this diagram that this white ball is lesser massive than the yellow one, and the yellow has made the space-time curvature curved in such a way that the white one is following that circular orbit. Similarly, in case of Earth, the bottom picture, here you can see that the moon is obliged to follow that path. So basically, Earth has made this changes around it in that such a way, Moon will follow this path automatically and it will circle around it like a satellite. So this is how Einstein formulated his first time he proposed that you can visualize gravity not as a force. You visualize gravity for a larger understanding as a space-time curvature. But for that, he has to pay a lot of effort, because how to formulate the question being, because we were very much comfortable in writing equation of motion where in the left hand side you have force and right hand side you have mass time acceleration, because it was the famous understanding of that time. So Einstein was also targeting to write down an equation of motion which will contain this curvature effect in it, and how to then come up with the energy source in that equation. So if I go to my next slide, it is basically telling us that, of course, after realizing that gravity can be treated as a field, he took one step further, that how gravity is basically can be also thought of as a space-time curvature effect. And then he has proposed, I mean, he actually derived this Einstein's equation of motion, the famous equation of motion of general relativity, where you can see that you have tensorial quantity. Because people tried, I mean, if you follow the book by Keith Thorne and Keith Thorne and that gravitational book by Keith Thorne, you will see that it was telling at that time people were asking that why it was not done by a scalar, why it was not done by a vector, why tensor was necessary. So actually tensor was necessary to formulate general relativity. So in the left hand side, you can see that you have some tensors, some second rank tensors are sitting along with the scalar. So you have a Ricci tensor, you have a Ricci scalar called R, you have G mu nu, which is basically the metric tensor, and this serves as the purpose as in the Newtonian GR as gravitational potential, which we can visualize later when we will discuss Schwarzschild solution. And remarkably, in the right-hand side, just see what is sitting. There is basically T mu nu, some energy momentum tensor. Now, energy momentum tensor means this is basically carrying the entire effect of the massive object. So this massive object, I mean, whatever is causing the space-time curvature due to what you are getting the left-hand side is basically encoded in the T mu nu. For the zero component of T mu nu, let's say T underscore 00, it is nothing but the energy density of that matter field. If you take Tij, the special component of that, it is nothing but the momentum density. So, sorry, that is nothing but the pressure. So this is how Einstein formulated his Einstein's equation of general relativity. Now, if I focus to the left-hand side more, basically he wrote the Riemann curvature tensor, a fourth rank tensor. He started from there. Riemann curvature tensor. Now, I will give you a simple example. Let's say you have two particles and you are letting them fall under the gravitational field. Now, as they get along, I mean, as they're freely falling, you can visualize that sometimes they're coming closer, sometimes they're going apart, and they're following the geodesic. As I said, that when a particle is freely falling under the only gravitational field, it means it is following its geodesic. Okay. Now, that geodesic deviation is basically encoded with the Riemann curvature tensor. So you can see that how Riemann curvature tensor is carrying the essence of the curvature. because your geodesic deviation, which is nothing but due to the curvature effect, the particle is sometimes getting departed, sometimes they're coming closer and falling under the gravitational field. So that geodesic deviation is proportional to the Riemann curvature tensor. So Riemann curvature tensor is the father figure of which is carrying the essence of the curvature. Then you reduce its tensor by contracting with the metric tensor. If you know little bit of tensor algebra, you can quickly understand. Then you get R mu nu. This R mu nu also physically depict the curvature effects. The Ricci scalar, that also depict the curvature effects. And from the Riemann curvature tensor, you can understand all that. So it was a brilliant equation which was equating in the left-hand side something like a curvature effect, but right-hand side you have the source of energy. So this is the construction of Einstein's equation. So Shona, do we have any question at this stage or?
No, nothing as of now. I have a question, Professor. We call it Einstein Field Equations, but we see one equations. Through study, what we found is that there are certain more partial differential equation 16, which is encoded in one single equation. If you can just,
Yes.
explain a little bit of that, why it is called equations, although we see one single equation.
Of course, of course. So basically, if you see the indices like mu nu, they all are Lorentz indices. I mean, if you think it like a Lorentz indices, they all run from 0 to 3, 0, 1, 2, 3. So you can actually write the series of set of equations like, let's say for when mu equals to 0, nu equals to 0. So you can write down r00 minus half. R is not carrying any index, so it is basically a scalar. So it is same. So R will remain intact, G will get G00 and hence T00. Similarly, if you go for the off-diagonal component like 0I, 0J or IJ, IIJJ, this is how you give birth to the plenty of equation from this. So if you run your indices from the dimension of the spacetime, if you are doing, let's say, five-dimensional theory, so this equation will look like some R capital Mn. I'm not using the Lorentz indices again. I'm using, let's say, some other indices, R Mn minus half R G Mn and equals to T Mn. And that Mn will run from 0 to 4. So then also it will be like number of equations depending on the space-time dimension. So this is what perhaps Shonok you were asking.
Thank you for answering. We can go ahead and follow.
So now the point is in the left hand side of this equation, let us take the very simple situation that when we do not have any source, if we do not have any energy momentum, like if we do not have any matter field or any sorts of source sitting in the right hand side, what we should get, what will be the solution of this Einstein equation. So now it can be shown that the vacuum Einstein solution in four-dimensional space-time is nothing but a spherically symmetric and a static metric, which is famously known as Schwarzschild metric. And this is basically a black hole space-time. Now, how you can see that it's a black hole space-time? This is going to be our observation for next two slides. Now, this kind of solution, it is of course a spherically symmetric solution, as you can see that the metric component like G00, 1 minus 2m by r, GRR, the 1 minus, I mean, all the prefactors of the coordinate dt square, dr square. So basically they are depending only on the radial coordinate. Neither they're depending on t, neither they're depending on phi. So basically, that is why it is a spherically symmetric solutions. And also it has the time translational invariance inbuilt in it. So that can be observed from here. If you transform this metric from t is going to t plus delta t, you'll get it back. So the point is, it is a very profound solution. And why it is a black hole solution? If you carefully note the condition r equals to twice m, so the r equals to twice n is suggesting you that this time the first term is fine. It is G00 is 0, still a finite number. What about the coefficient of dr squared? This is a divergence at r equals to twice n. So this is suggesting you that geometry has some peculiarities at that r equals to twice m surface. So that is called basically the event horizon of the black hole. And it was shown that this kind of feature, I mean, of course, this r equals to twice m feature, one can handle this divergence can be handled by changing the coordinate transformation. However, the point is, it is basically telling you that the determinant of the metric is also going to be zero. So therefore, there lies a kind of surface which is a one-way member, which is a one-way surface basically. If any particle which is crossing the event horizon, it will never be able to come out, at least classically. So classical general relativity is telling you if your any particle is going, it's crossing r equals to twice m surface, then nothing trace of that particle can come out. And this is similarly true for the light. Okay. So this is how the Schwarzschild black hole solution was formed. Now, what about the another divergence at r equals to zero? That is basically a physical singularity. That singularity cannot be removed by performing any sort of coordinate transformation. Although the r equals to twice m divergence like feature you can remove uh, just going to another coordinate transformation, but r equals to 0, 1 you can't. And for that, there is a nice quantity which is parameterized called the Kretschmann scalar. It is nothing but the contraction of Riemann curvature tensors, r mu nu alpha beta lower, r mu nu alpha beta upper. That gives you something proportional to 1 over small r. And if r going to 0 is showing the divergence, if your Kretschmann scalar diverges, then you are gone. That's a physical singularity. So any particle which is entering the region r equals to twice m, it will absolutely crush by the gravity and will hit the singularity. Now, also another thing you can note that you may ask me that crossing the horizon, why you are saying that the particle cannot be static within that space-time? No, because the moment r is becoming less than twice m, what will happen? The dt squared coefficient will become positive and the dr squared coefficient will become negative. So the time like, so the if you now put dr square equals to 0, basically your time like coordinate became space like and space like became time like. So it became flipped. And that is why it has to, so it is predicting that it has to hit the singularity. There is no option. You cannot imagine a slice within the r less than twice m region, which is static over there because your t becomes space-like and t is ever evolving. T is always minus infinity to plus infinity. It has to hit the horizon, no option left. So this is why I'm saying nothing can escape out of the horizon. So that is why it's a black hole space-time. Now, if I go to the next slide, so this is how a black hole look like by the let's say space telescope, James Webb Space Telescope. And if I just make a schematic diagram of this spherical symmetric space-time, it will look like mine. I mean, of course, you have r equals to 0 singularity, and you have r equals to twice m as event horizon. R is going to infinity is basically an infinite distance apart from the horizon and from the black hole, which we say asymptotically at asymptotically large distance. So that is also very interesting. At asymptotically large distance means where small r is going to infinity. And if you just take the small r going to infinity limit of this metric, you will land up with the Minkowski space-time. This is nothing but minus dt square plus dr square and the two spheres sitting over there. So this is how you can imagine that why the asymptotic observer, where we are sitting and trying to see that whether black hole radiates or not, whether black hole is present over there or not, we are basically asymptotic observer. If you go close to the black hole, then you are becoming something else observers. So now after this is basically the light cone manifestation of the black hole. Now, when I say that you are basically trying to remove the singularity or the diverging, annoying diverging feature at the horizon, which is basically a coordinate singularity, that can be removed. And now if you want to remove that uh, singularity at horizon, you can basically make perform many coordinate transformations, which are very potential candidate to realize this fact. Number one, TR was my usual Schwarzschild coordinate. You can go to something called tortoise coordinate transformation. You can then again go to Eddington-Frankenstein coordinate system, and then you can go to the Kruskal-Jaeger coordinate system. This Kruskal-Jaeger coordinate system is basically our candidate because this is basically a very nice candidate to remove the singularity of the horizon, at least, but not the physical singularity at r equals to 0. So now, if I just try to see the light cone diagram in, let's say, Eddington-Frankenstein coordinate, mostly in the VR plane of the Eddington-Frankenstein, just stick to the point that we know how to draw light cones. So light cones is nothing but where all our physical events are confined. This is special relativity taught us. You even can write down, draw light cones by just write down the Minkowski metric, and you can at first define the null rays for d square equals to 0. Then you define d square less than 0. And if your metric signature is minus dt square plus dx square, you can get the light cone structure, and either way around. And also you can define the space-like events. So this is basically the light cone of an observer who is, let's say, or a particle who is approaching the black hole from asymptotic distance. You can see that that slope of the light cone is getting changed, of course, because of the gravitational effect. When you are going close to the event horizon, you are basically getting exposed to the high gravitational effect, which you didn't feel when you were just an asymptotic observer. So when you are approaching the surface called horizon r equals to twice m, you can see that this light cone is completely inside the black hole event horizon. And light cones means this all events has to take place within this region only, which is already entered the region r equals to twice m. And those all events has no option other than to hit the singularity, r equals to 0. So this is how you can visualize that why r less than twice m will not emit any information classically. So if I remove my cursor, then is it visible on the screen
Yeah,
or
it is
not?
visible. No,
Okay,
it is
so
visible.
basically, if you take time-like trajectories here and let time evolve progressively, then you can see that all those time-like events will eventually hit the singularity. That's it. So that is how you can visualize the black hole space-time. So at this stage, do we have any questions, Shona?
No, right now we don't have. Professor, I would like to ask you at this very juncture, what you are explaining, what is the role of the Roy-Choudhury equation that comes in? In brief, if you can just tell us.
Uh, at this stage, for the Roy-Choudhury equation, at this stage, I will not be able to say
Okay, fine.
much,
Let
but
us go ahead. Yeah,
yeah,
let us go ahead with the
okay,
flow. Okay, fine. No
okay,
problem.
thank you. So now, after realizing this, another important thing comes to our mind that all this coordinate actually this black hole coordinate the transformations of all these transformations what we did, let's say the tr or the tr star uv and u tilde b tilde, all these you can see they have certain ranges, and those ranges are mostly minus infinity to plus infinity, at least for the Kruskal-Jaeger, definitely. So then Rosa Penrose suggested us that whether we will be able to somehow visualize this entirely infinitely spanned coordinate system. I mean, other than using this infinitely spanned coordinate system, whether we can actually confine this entire treatment to a very much like, let's say, finite domain or finite region, whether we will be able to map this entire coordinate transformation within a finite region.
Ma'am, we
So
have a question coming up. Sorry to interfere, but I
no,
think we can
please go ahead.
take it up
Yeah.
later. Somebody called Physics is asking, ma'am, how Hawking and Penrose used work of Roy Choudhury? I think we can.
Okay,
You
so
can,
can we just postpone this question for the latter half
okay, yeah,
because
for this.
till now,
Yeah. So we
yeah,
will come to this physics, don't worry.
sure.
Yeah,
Please,
yeah.
please remember this. Okay, so now as we can see that in case of the Penrose diagram, it is very much important to understand that why it was necessary. It was necessary to visualize the space-time within our realizable domain. So how we can bring down infinity to a finite region. And in order to do that, let us just simply first of all take the simple Minkowski space-time Penrose diagram. So if I just write down the Minkowski metric, which is you can see over here that it is dA square minus dt square and all that. So here you can see that this is simply a Minkowski flat spacetime metric. Of course, it is in the spherical polar coordinate. The spatial part is in the spherical polar coordinate. And that is why r squared d omega squared kind of term came up. Otherwise, it is nothing but a dt square plus dx square plus dy square dz square. So now if I perform certain coordinate transformation, let's say this kind of coordinate transformations. I'm not going to the very details of this, but you can see that I have performed some coordinate transformation here. So if I perform such coordinate transformation, then you can actually see that this entire space-time will look like this. It's just like a triangle. So if you see that after performing the coordinate transformations, some steps of coordinate transformations, if you follow those, uh, you can see that after all, when you get this entire space-time metric in terms of capital T and capital R, you will get the space-time look like a triangle. And here you can see that the points like t equals to 0, r became a basically capital R. It is now it is manifesting an angular coordinate like r equals to pi. And your metric is basically looking like minus dt square, d capital T square. Please don't get confused with the small t and the small r. Okay. So this is basically capital T, capital R. And here you can see that sine square is carrying the argument of capital R. Capital R here is an angular coordinate now. Okay. I have performed a tan uh, coordinate transformations with tan theta kind of thing. So now your entire space-time look like in the TR plane like this. Now, what this tells us? It tells us very nice some stuff. So for t equals to 0 and r going to pi, your known small t and small r is basically telling you that t is finite and r is going to infinity. So you performed coordinate transformation, you brought it down to the capital T, capital R. Now, when capital T is 0 and capital R is pi, it is basically mapping to your known small t and r as t finite, r infinity. But please try to realize if r is infinity, that means it is telling you that this kind of particle will reach to infinity within a finite time. That means infinite velocity, r by t, right? Your t is finite, but r is infinity. But that is not allowed from the special theory of relativity. So that is basically a space-like point. And that is manifested in the Penrose diagram as t equals to 0 and r equals to pi, this point. This point is absolutely inaccessible by us. We are time-like particles. Our velocity should always obey the special relativistic treatment, right? So this is how all the other points like t equals to pi, r equals to 0 and all such will manifest some important points on the Penrose diagram. So for t equals to pi, r going to 0, it is basically telling you t tending to infinity, but r is finite. This is all right. It is telling you the future infinity, that you are progressing towards the future and r is finite. So it is actually consistent with the special relativity. So try to understand the causal structure, what Penrose brought in, which was not that visible in case of the, let's say, minus mu to plus infinity span. Now it is very much visible when boils down this entire diagram to this finite region. So basically, this is telling you that, okay, this is fine. It is basically that when one takes a time like infinity is going to the time like infinity, where normal particle is going towards the future. Next, let's say t is going to minus pi, r is going to 0. It is manifesting t is minus infinity, small t, and r finite. This is also allowed, and it is telling you it's a past event. It's a past time like infinity, from where everything originated, let's say. Okay, so just try to understand the causal structure, that when I'm saying now, if I straight away go to the next here, so all the time like event originated from I minus and will end up on I plus. I0 is the space like point, inaccessible. Scry minus, scry plus, which is basically curly I and curly I. This is actually pronounced as script I. So scry minus, scry plus is basically the path of the light rays. So they basically known as, so this scry minus is basically called the past null infinity. Null because you are talking about light. And light always follows the space-time interval as d square equals to 0. Time like follows d square less than 0. Space like follows d square greater than 0. So that's why whenever I will speak about light, I will either say light like or null. So they are null past infinity and null future infinity. So this is how Penrose actually confined the Minkowski spacetime can also be portrayed. This idea you can absolutely generalize for the Schwarzschild Black. You perform coordinate transformation from the tortoise, Eddington, Frankenstein, Fuskel-Zecke to the Penrose, and you land up to the, okay, there are some few points here I want to say. Suppose when I was talking about the light cone, so this is basically the I minus to I plus, that a physical particle is confined within the light cone is basically progressing from I minus to I plus. So it is a time-like picture of this Penrose diagram by what a physical particle is going through. So this is how I have discussed certain points over here, which you can just look into. So here, if I have anything to mention, just let me quickly say, see over here. Uh, okay, so now if I just come to the
We have a
manifest,
question. We
sure,
have a
sure,
question
please.
from Indranath Bhattacharya.
Yeah.
Does tidal effect vanish in the event horizon of Schwarzschild black hole? The neighborhood of event horizon is Rindler spacetime, which is basically flat.
Yes, yes. This is a very nice question. So the point is, of course, the neighborhood of the Schwarzschild black hole is Rindler spacetime, but in two dimension. Okay. So if we take the two-dimensional approximation of near to the event horizon region, we will get the Rindler spacetime. So of course, then you can say that it is like a flat spacetime. But this doesn't mean that the entire, but globally, the curvature effect's gone. This is not actually the correct manifestation. The point is, if I go near horizon limit of the Schwarzschild black hole, then only we can see that in two-dimensional space-time, it is exactly in 1+1 dimension, it is exactly looking like a linear. And it was a direct motivation for us that if in flat space-time, I'm able to see Unruh radiation, then why not in curved space-time or in the near horizon region, we will see black hole radiates. So of course, it is a direct motivation from there. So, but globally, we cannot say that the tidal effect will be vanishing at that point. I hope I answered the question. Is there any question along that line? Okay. Sorry, Shonok, you are muted. I
You
couldn't
can
hear.
continue with the presentation. If I have any questions, I will just let you know.
Okay, thank you. So here now, if I just try to understand that how Schwarzschild metric will look like, how Schwarzschild spacetime will look like in case of the Penrose diagram, then this is how it looks like in case of the Penrose diagram. So entirely let's say Schwarzschild, in case of Schwarzschild coordinate T and R, for the Schwarzschild patch, T runs from minus infinity to plus infinity, R runs from 0 to twice m to infinity. So to realize all those infinities within a finite region, you perform Penrose coordinate transformation from the Kruskal-Decker onward. And then you can actually produce this kind of diagram. So here, similarly, just try to imagine the Minkowski discussion. Here also we can have a I minus I class, which actually will be followed by all time-like particle. Now, time-like particle from I minus to I plus, they can also access this region. But once it is entering within the R equals to twice m surface, no light cone will be able to produce any events which will be the outgoing modes. So this region, if I just tag it as region 1, 2, 3, 4, then region 1 to 2 is quite accessible. That is not a problem. But from 2 to 1, it is not possible. So I0, again, it's a space-like point. And this wedge, I mean, this number 3 region is just a mirror image of this. So it is also spatially, it's a space-like wedge. So this is how the Penrose diagram was done in case of the Schwarzschild metric, where you can see that R equals to 0 is coming over here. This is a future singularity, where all the future going time-like trajectories will end up once it is inside the R equals to twice m surface. And this is basically a past singularity from where maybe the events will be generated from R equals to 0. So here in this wedge, all the events, they can just only go out in the region 1, in the region 3. But nothing can come in within this region 3. So basically, R equals to 0 is the past singularity from where events can be generated, from observer can start with. And it can send signal to wedge 1, wedge 3, and of course, wedge 2 as well. So the point is, this region, somehow it resembles with a white hole region. And this is basically a space-like region. And this is I minus to I plus is telling you that all the time-like events will go from I minus to I plus, and they are free to go even penetrate R equals to twice m. So this is how the black hole space-time can be visualized in Penrose diagram. So this is, up to this, we have addressed so far that how basically we can see the we can see basically uh, the Penrose diagram and the causal structure of Penrose diagram. Just try to understand some subtleties. The region 1 to 2 is accessible, but 1 to 3 is not accessible. These two are not accessible. So they are causally disconnected because one is time-like and another is very much, I mean, one is basically depicting you the very much time-like events. And this I0 here, I0 also can be also sitting here. So this is how the causal disconnection in the Penrose diagram can be visualized in case of the Schwarzschild black hole. So now let us just come, So let us just come to the next section. Okay, so this is how we define all this parameter in the Penrose diagram. So at this stage, if we do not have any other question from the classical part, is it all right that I move
Yeah,
on
we
to
can
the
go ahead with the
relativistic?
relativistic part. Yeah, I mean, the quantum part. We don't have any question as of now.
Okay. So here, in this case, what we are going to understand, let me tell you one thing, that before I start Hawking radiation, I will try to motivate something which already one participant beautifully asked about the Rindler space-time near the Schwarzschild black hole region, that why he actually mentioned about the Rindler. It is important because in flat space-time also, we can have horizon. Now, how we can have horizon in flat space-time? So this basic question is basically originated from the very core point of let's say, observer dependence in fundamental physics. So observer dependence in fundamental physics is basically encoded with special relativity. We all are aware the time dilation, length contraction, simultaneity is basically everything is coming from the special relativity, and those are observer dependent phenomena for the two inertial sets of observer. Of course, no non-inertial. Now, again, we complicate our life by asking the question that what would happen if we bring in the acceleration? What would happen if we just try to frame a non-inertial reference frame? So that means, let's say the simplest situation, uniformly accelerated observer. Now, if I ask this question, this straight away leads me to the Rindler transformation. So Lorentz transformation is the story of inertial reference frames. Rindler transformation is the story of Minkowski to the basically t or your known t x y z to the Rindler coordinate where the Rindler coordinate is telling you that I'm the coordinate who is uniformly accelerated. I'm not inertial. So my coordinate system will be depicted with the Rindler coordinates. Those are, let's say, some tau time, some xi space like. Okay. And y, and let's say for convenience, y and z they kept constant. In case of the tx yz, only t and x, let's say, gets the transformation. Y and z kept constant. In this coordinate transformation, if you see carefully, you will see immediately that the equation what this observer is following, if it is visible on your screen, it is nothing but x square minus t square equals to 1 over a square. This 1 over a, here small a, is the proper acceleration of that observer. Okay. This is basically a hyperbola, the equation for the hyperbola. Now, if I just take you to the diagram, because diagram speaks a lot than the equation. So, in your Minkowski idea, t square minus x square, the space-time interval is nothing but t minus t prime whole square minus x prime whole square. You have this bold red lines as the light cones. Now you have transformed your Minkowski space-time to something called tau and some xi. Now, as I'm talking about the proper difference frame, xi is put to 0 or you can take constant. So everything is transformed in terms of, let's say, the proper time of the accelerated observer in case of the Rindler. And he is accessing some path which is following the equation t square minus x square equals to 1 over a square. It's a hyperbola. And if you see carefully, this hyperbola equation t square minus x square equals to 1 over a square, along with this line t equals to x, they do not have any common solution. They cannot intersect each other. They are asymptotes. No matter how much you extrapolate them, you cannot have any common solution for this two. So basically, for an observer who is riding on this blue hyperbola, is the t equals to x line for that observer is a horizon, because he cannot meet that line. He cannot see anything beyond that line, because if he wants to see something beyond that line, he has to intersect this line and see beyond. For inertial observer, he can access the whole space-time. T equals to minus m to plus infinity, x equals to minus m to plus infinity, because he is sitting somewhere here. But who is riding on that hyperbola, for him, the entire Minkowski space-time is truncated only to this wedge. He cannot see anything beyond t equals to x. So not only in the curved space-time, you can have the horizon-like structure, or not the event horizon, but a horizon, even in the flat space. So this was the charismatic feature of Rindler transformation. And this will lead us to the extraordinary idea, which is basically known as Unruh effect. Now, of course, diagrammatically, I will try to motivate the entire scenario, and then, of course, the detailing can be done. So if you see that the Rindler transformation did what? It actually compartmentalized the entire Minkowski spacetime in right Rindler wedge and left Rindler wedge. A person who can access left Rindler wedge, he or she will not be able to communicate with right Rindler wedge because t equals to minus x line is the horizon for that observer. So you have two causally disconnected patches in your known Minkowski spacetime, and no time, no light signal can be communicated between them. So keeping this in mind, let us take that our observer is confined within the right Rindler wedge. And then, of course, we will come to the next question, that for for going further, we now need to introduce that, as I said, no light signal can cross. So when I say light means, you will immediately tell me that now, Ashmita, you're bringing in particle. Of course, I'm bringing in particle. Now I'm bringing in not particle, I'm bringing field. Let me go to the most basic entity. What we understood till date is as a field. Okay, so not quantum mechanics. I'm going to do quantum field theory now onward. But why not? Why not quantum mechanics, and why quantum field theory? So basically, you can ask me that you started with the observer dependence. Yes, observer dependence, length contraction, time dilation gave us beautiful outcomes. So similarly, people started people started asking, what is the concept of vacuum? Is the concept of vacuum state, or the definition of vacuum is unique? Is it not subject to the observer? We don't know. We didn't know before this Unruh effect came in the picture, because we were always thinking that no, vacuum is a no particle state, of course, but with respect to whom? It is never specified. Which detector is telling you that vacuum is no particle state? So now, is vacuum is also, I mean, vacuum also do not possess any unique definition. Let us come to that point at this stage. So here you can ask, at first, when I bring in the vacuum, I am actually talking about, let's say, the vacuum of a scalar field. So when people started posing the queries, doubts that whether vacuum has a unique notion or not, then I brought the quantum field theory in the picture, or let's say the field theory in the picture. So when basically quantum mechanics and special relativity, we try to combine these two, we get the outcome as quantum field theory. Because if you remember your Schrodinger equation, you can quickly see that in Schrodinger equation, at first it is a one particle system equation. And here t and x, you have a double derivative of x and you have a single derivative of t. So t and x, of course, is not treated equally. They are not treated equally. But if you bring in relativity, you have to treat t and x at equal footing, because it should be fall under the four vector notion. Now, if you bring in special relativity, everything becomes x mu, where the zeroth component is time. But Schrodinger equation never support that. Another beautiful thing is the particle number. When you bring in quantum mechanics, within the quantum mechanics framework, you bring in special relativity. What happens? Just let me tell you schematically. Now, if you bring in that, just if you follow some of my equations over here, Heisenberg uncertainty principle from quantum mechanics. It tells you delta x delta p greater than equals to h bar. So delta x delta p is the standard deviation in the measurement of x and p. And your precision has to always follow this. Now, if you bring in special relativity, that means you bring in the dispersion, you have to bring in the dispersion relation, because now energy and momentum also you have to write down under the same umbrella as a p mu, As x mu, it has to be p mu. P0 is the energy, and all the p vector, 3 vector, is linear momentum, and hence the dispersion relation. So if it is a very much if it is a very highly relativistic particle, you can actually do this just very simple algebra and show that E is near about PC for relativistic particle. Now you substitute your delta P in terms of E. So your uncertainty principle with this replacement now became delta E greater than equals to some CH bar divided by L. So L is basically a length where your particle is confined, right? So this is telling you that if you decrease L beyond H bar by MC, so that lambda, you will get your delta E is greater than equals to the rest mass of the particle you started with. That means you can give birth to another particle. So that means you started with one particle state, but as you brought in the special relativistic concept, it is basically the swirl of all the particle who are swimming around that one particles with which you started. Schrodinger equation cannot handle many particles. So that is why this is the discrepancy when quantum mechanics is clubbed with special relativity. Now people brought the concept of field, which is absolutely, Maxwell showed us that the field concept is absolutely compatible with special relativity. And therefore, the field quantum field theory came up. So if you just follow this schematic, you will quickly get why it is not sufficient. Now, if I quickly go to this, not spending much time over here. So that was around and one particle, you can have many particles. What about the vacuum state? Manifestly, vacuum state has no particle. But within the vacuum state, if you design some region which is lesser than that lambda, you can have the particle-antiparticle creation in the vacuum as well. But how will you justify observationally that it is a no particle state? Because then you have to take that it's like a fluctuation. Continuously, particle and antiparticle pair is producing and quickly annihilating with maintaining the Heisenberg uncertainty delta E delta T greater than H bar. So in case of the vacuum state, always the particle antiparticle creation and annihilation is going on. That is called famously the vacuum fluctuation. This also gave birth to Casimir effect, do not forget. So the point is Casimir effect is already observed. So we cannot doubt this. So the point is the vacuum fluctuation is happening due to the relativistic effect where particle-antiparticle pair is getting produced, getting annihilated, produced, annihilated. And hence the net effect is a no particle state. But please don't forget the fluctuation is not zero. If you take the expectation value of that fluctuation, that means the correlation of the fluctuations, those are non-zero. So this lies the core concept of Unruh effect. Now, if we just straight away go to the picture diagram, this will tell you all.
Oh,
So
ma'am,
let
we
us
have a
first.
question, small question. It
Okay.
is telling that, ma'am, how de Broglie used lambda equals to h by p from equal to mc square and equals to hf, as one is relativistic and one is quantum. So how he equated before Dirac developed the relativistic quantum theory?
Okay, so how why it is why you are asking why you are saying that it is basically equated? I mean, I don't understand where de Broglie has equated this. I mean, can you
Yeah.
just
So yeah, physics, I would request you can mention
so
actually the point
lambda
where he
is
equated
yeah.
it. Yeah.
Yeah. So lambda equals to h by p. Of course, h bar by p is the de Broglie hypothesis for all we understand. But of course, E equals to mc square is not directly never incorporated in here because, of course, that is a relativistic concept. And I have never seen in quantum mechanics where we directly use this. I mean, the context I used, there you can see that when I'm actually taking the particle to be relativistic, and I can equate E equals to PC. Similarly, what you're seeing E equals to mc squared, that is the rest mass energy, and I'm saying it is very much relativistic so that you ignore the rest mass part and you get the PC, E equals to PC. So that is how I equated delta P with the delta E along with the C, of course. But I really don't know that within the quantum mechanical framework where we have exactly included this. So if
Right,
you
you
have,
can go ahead. Yeah, if the viewer can,
uh-huh,
reconfirm. Otherwise, we
huh,
can go ahead with the. You can go ahead with
sure,
the rest of the part. Yeah.
okay. So here, if we just focus to this diagram, Unruh effect will be clear to you, that I promise. Just remember t equals to x, I said it's a horizon for the blue observer, the pink one who is riding on that blue curve. And the red observer is an inertial observer for whom t equals to x is no horizon. He can access the whole space-time. But for the purple one, the Rindler observer, it is actually t equals to x is a horizon. Any event taking place beyond t equals to x, the purple one won't be able to see. Now, if I take that Rindler observer, let's say this accelerated observer is probing a vacuum state of a scalar field. And also I have kept an inertial detector in the vacuum state of a scalar field. Now I'm talking about scalar, but you can just picturize it as a photon, which is consistently giving you a E plus E minus pair creation and again annihilation. Again pair creation, again annihilation. That means vacuum fluctuation. You take the vacuum state of a photon. I have no problem. Okay. Because this diagram is done in that way. That a photon is continuously creating E plus E minus, again getting annihilated, because that is how I explained that vacuum fluctuation should be there in quantum field theory. Now, for an inertial observer, this vacuum fluctuation is a very normal thing. He will always see that particle is getting created and annihilated quickly. Okay. But for the Rindler observer, if this annihilation is falling beyond t equals to x, this 2 e minus e plus, he will never see that e minus e plus is annihilated. He will see a real particle popped out from the vacuum state. So this vacuum fluctuation is continuously going on. For this Rindler observer, any vacuum fluctuation happening in this side of the t equals to x is fine, no particle production. But there is a non-zero probability that some vacuum fluctuation, if it is falling beyond the t equals to x line, Rindler observer will see it as a real particle production. This is known as the Unruh theorem effect. So of course, you can absolutely write down a quantum field theory with respect to this inertial observer. You have to define the vacuum state corresponding to this inertial observer, which is, let's say, Minkowski vacuum, no particle state. And for this, on the proper frame of this hyperbola trajectory, you have to define another vacuum state, because his quantum field theory is not same like us. His entire space-time is confined only within the RRW. He can access only a patch of Minkowski space-time. So if you want to define the quantum field theory on Rindler trajectory, you have to define a Rindler vacuum corresponding to the time, like coordinate of this fellow. Now you can ask me why you just arbitrarily mentioned time, because vacuum state, in the definition of vacuum state, time translational symmetry has enormous role. If you have time translational symmetry, you can actually define a positive energy particle state. That I can show you schematically how. Very rough, sketchy idea. So the time coordinate of the Rindler is not similar as small t of Minkowski. They do not have any time translational invariance between these two coordinate system. Minkowski metric is not at all time translational invariant under Rindler. The Rindler metric is completely different. So you have to define another vacuum state with respect to this. So this is the core concept of Unruh effect in flat space-time. And that is why when the participant asked about the Rindler, it was a very nice connection. The black hole space-time can be reduced to the Rindler space-time in 2 dimension. And then people had a direct motivation that why black hole cannot radiate. Black hole should also radiate. If in Rindler space-time I can see this, why not my black hole? So now onward, if as there are certain remarks which I said, which I mentioned over here, that if I see real particle production, that means it's particle radiation. It will give me a temperature as well because it's a radiation. And there is a, of course, entire mechanism of establishing Unruh effect. If I see, then you can see that the Minkowski vacuum state is basically 0M, where you have, let's say, this is the Minkowski vacuum state and this is the Rindler vacuum state, as I wrote here. And then now, how to understand this particle production mathematically? This is done by the Bogoliubov transformation.
Okay, we have a question, Professor, coming up from Dev. He's asking, will the interpretation of particle state be different in the vacuum taken for curved space-time?
Yes, I mean, the interpretation of the Unruh effect is basically entirely the flat space-time phenomena. So the particle notion in this concept is not at all same as the Hawking radiation. It is similar to some extent, similar. So Dave, I just want to tell you only this part that particle state be different means you are analyzing the entire thing in flat space-time. So in this way, the particle production, if you're taking the photon, you will see the photon as a quanta. But the mechanism involving in this two kind of particle production is completely different. Although we have a direct motivation, but these two mechanisms are different. One space-time has curvature, and this is simply a flat space-time result, but the produced particle quanta will be still the same. It depends on the matter field with which you're working. If you're taking a fermion, if you're taking a whether you're taking a gauge boson, whether you're taking a scalar, so accordingly, this quanta will emit. So this is what the concept. The particle quanta by characteristics will be same, but the mechanism is absolutely different. You have a direct motivation. That's true. Now the Bogoliubov transformation comes in the picture in order to relate this consequences of between these two vacuum state. Now, if you see that how this comes in, I mean, if I do not go in the detail of this, I don't know that how much time also I have shown up. This is
No,
a
we
very
can go ahead. It's going absolutely great. We are all watching around 30 to 33 viewers still are online and they're watching it. So it's a very intensive discussion. Please go ahead.
my, my pleasure. So now, if I just focus on the two-dimensional space, then just for simplicity, fellas, because trust me, it can be done in 3+1 as well. So if in the 1+1 dimension, this is the Klein-Gordon equation for a simple massless scalar field. I have taken the simplest example. Now, quantum field theory tells us that we can decompose field in terms of the creation and annihilation operator along with their mode decomposition, where modes are like positive energy solution and the negative energy solution, where which Dirac formulated as his antiparticle. Now, with this decomposition, you can straight away see the annihilation operator small a. Let's say this is the Minkowski decomposition. I have decomposed scalar field phi in terms of Minkowski quantization. So Minkowski quantization is basically in terms of the creation and annihilation operator. And here you can see that the annihilation operator acting on the vacuum will straight away give you 0. So this is the Minkowski annihilation operator defined on the Minkowski quantization for an inertial observer. AI dagger is the creation operator acting on the vacuum state. It will give you one particle state, where that linear momentum can take any value from 0 to infinity. This is the quantum field theory core concept of QFT I'm getting into. And also they follow the commutation relations. You can have a rough idea from the creation and annihilation ladder operator from the quantum mechanics, how we treated harmonic oscillators.
One question coming up from
Yeah,
Devman. Uh,
sure.
will statistics be affected if we consider the vacuum curved spacetime?
I don't understand the question. I'm sorry, because what spin statistics has to do with the vacuum? I'm sorry.
Yeah,
Because the vacuum is something, it's a state of a particle which we can define as well as in the flat space-time and in the curved space-time, right? So the spin statistics is basically it's a quantum character of that field. It has nothing to do with the vacuum defined in curved space-time or in the flat space-time, as long as my understanding is coming up.
yeah, sure. Just one quick note, a very important person is just joined in, Dr. Madhukrishna Chakraborty, and she is telling, please continue. It is going great, really. Thank you, Doctor. And just a quick note to the viewers, Dr. Madhukrishna has been one of the great speaker in general theory of relativity, and she has come as a guest speaker on my channel, Physics for Students also. Professor, we can go ahead with the rest of the part.
Great, Mother Krishna, having you here. So, uh, and thank you for your support. So, basically, we can have the commutation relation as well between the creation and annihilation operator as well. So, this is the for the Minkowski space-time I'm talking about. Now, similar thing you can do for the Rindler. Let's say this one, this blue one, phi tilde tx. You can actually also have a Rindler decomposition by the similar means of this. I mean, I wrote it somewhere in the below, perhaps, which is not visible, maybe. But the point is, you can also have a Rindler annihilation operator along with the Rindler mode, Rindler creation operator along with the Rindler negative frequency mode. So phi can be decomposed both in terms of the Minkowski and both in terms of the and as well as in terms of the Rindler. Now, if you straight away go to the concept of, let's say, if these mode decompositions, I mean, if I have the Klein-Gordon, let's say the complete set of Klein-Gordon solutions, let's say we have two sets of Klein-Gordon equation. It's, of course, a second order differential equation, the Klein-Gordon equation. So if we have two sets of different solution of the Klein-Gordon equation, then their linear combination can also be the solution of the field. So in keeping in that mind, basically, let me now write down. This is the Minkowski quantization AI. These are the Minkowski modes. This is the Rindler quantization, and these are the Rindler modes. If I R and if I R star. So R and M, they are symbolizing Minkowski and Rindler. Please note that Rindler annihilation operator will actually, the Rindler annihilation operator while acting on the Rindler vacuum will give you 0. But while it is operating on the Minkowski vacuum, will not give you 0. So here we have two distinct set of mode solutions because both are accessing the same scalar field, your Rindler observer as well as the inertial observer. And you can expand in terms of both of their mode solutions. You can define both of their QFTs. You can define both of their creation annihilation operator. You can define both of their vacuum states. But Minkowski annihilation operator acting on the Rindler vacuum will not kill it, and vice versa. So therefore, the whole purpose is now to write down that how Rindler mode can be written down in terms of the Minkowski modes. Because I told you, both are two complete sets of solution. So their linear combination eventually will give you the another potential solution. So here you can see that some alpha and beta coefficients came up. They are known as the Bogoliubov coefficients. And this transformation is known as Bogoliubov transformation. It is vice versa. You can write down Rindler mode in terms of Minkowski with the help of Bogoliubov coefficients. You can write down Minkowski solutions with respect to the Rindler using the Bogoliubov transformation, using the Bogoliubov coefficients. Similarly, you can write down The creation and annihilation operators, AI and BI, both are different. AI is for inertial observer, B is for accelerated observer. You can combine them as well using the Bogoliubov transformation. So this is the very nice transformation which is bridging between the two quantization scheme. Right. So now if we go to the next slide, here comes the catch. Calculation of the number operator, that is what is left. Nothing is left. We know that what is number operator? It is nothing but a dagger A. Just remember your harmonic oscillator ladder operator using ladder operator. So if you take the Minkowski number operator expectation value with respect to the Minkowski vacuum, of course it will give you 0. Vacuum is a no particle state. You calculate number operator, Rindler number operator on Rindler vacuum, sandwiched between Rindler vacuum, 0. But it is not ensured that if you calculate BI dagger BI with respect to 0M, it will give you 0. No, it is a non-zero. This is a straightforward mathematics is showing it is exactly equal to the mod square of one of the Bogoliubov coefficients. So basically, Rindler number operator calculated with respect to the Minkowski vacuum is non-zero. And that means particle radiation. So basically, this Bogoliubov transformation is telling you this is basically like a Planckian distribution of black body. 1 over e to the power h nu by kt minus 1. That means thermal bath. And this T, the temperature of this bath is directly proportional to the acceleration of the Rindler cell. You increase acceleration, the temperature of the thermal bath will increase. So this is the mathematical treatment, what exactly I tried to manifest through these few steps. I know this is very much maybe not that clear to some of you, but I'm just trying to motivate you to tell that perspective differs, not even in our life. Of course, physics follow it. I mean, you cannot deny that. The perspective of an accelerated observer is not same. So the vacuum definition is not unique. The one I'm seeing as vacuum, if you are a Rindler observer, you will say, no, I just saw some particle popped out. And you will see the thermality. This feeling of thermality now you can have in many ways. If you know thermal field theory, you can do the mathematics in a different way. If you know something, if you know how to write down the density matrix and all such treatment, you can do it in a different way. This is one of the treatment. If you know the KMS condition, you can do something in a different way. So this is the Unruh's direct derivation. Now the application part people designed, and Dewitt is the main person called Unruh Dewitt detector. So that I have not done very
Okay, we have
elaborately.
another question coming up,
Yeah.
Professor. Does the Bogoliubov transformation provides the invariance of Hamiltonian of the system?
Uh, Basically, the if you see the Hamiltonian of the system will not be changed. The Hamiltonian of the system will be intact. I mean, uh, yes, the Bogoliubov transformation will not change the Hamiltonian of the system. Hamiltonian of the system is fine because you see, it is just a free quantum field theory. I have not even introduced any interaction. I started with a free Klein-Gordon field, that too massless. So Hamiltonian Lagrangian of the system is not at all affected. What you did is that you have just taken the relation between the two sets of two sets of mode solutions. So Bogoliubov coefficients will keep that intact. Yes.
We have another question, this time from Dr. Madhukrishna. Is there any observational evidence of QFT other than Casimir effect?
Okay. Madhukrishna, the observation of QFT is everywhere, the standard model of particle physics. Absolutely. So, but I think you actually tried to asking the observation effect of unrefueling effect, maybe, if I'm not wrong. So because the entire standard model of particle physics is based on the quantum field theoretic idea. So yes, and if you ask me about the observational effect of the underfueling, not yet, but actually people are trying to see this in a several setup. Like recently, I was reading a paper where superconducting circuit was using people were using superconducting circuits as a probe of the Unruh effect or the Unruh detector. So yes, this is a very nice idea doing this. Yeah.
We have another question coming up from Abhijit Kumar. Ma'am, Bogoliubov transform is like raising operator, which helps to raise the energy of particle.
No, no, fella. Please try and understand, Abhijit. Bogoliubov transformations, you are saying itself, it is a transformation, right? So basically, it is a transformation of the two sets of mode solutions and two sets of, let's say, creation and annihilation operator. This is not something which can elevate the energy of the particle. It is not elevating the energy of the particle. So this has only the role to make the bridge between these two quantizations.
Okay. We have another question coming up from MD Explains. How is it possible that we deduce quantum effects of gravity without having real working theory of quantum gravity?
Okay, so the point is, MD explains that we are, at least here in this entire discussions, I'm not going to do this quantum gravity at all. I will do rather semi-classical gravity. The point is, I am, it was the achievement of Hawking who actually shown that I mean, without doing the hardcore quantum gravity effect, we can still visualize the quantum effects from the classical gravitational background. So you can say that this is the starting point or one of the motivations of doing the full consistent theory of quantum gravity. I completely agree with you. This is, of course, an effective theory. This is not the fundamental one, like Hawking radiation. Of course, Hawking radiation, the treatment of Hawking radiation is not the fundamental theory. It is an effective theory because here we are treating general relativity as classical at all. But you have put arbitrarily a quantum field in that classical background. So basically, you have done a semi-classical gravity theory. So it's an effective description, but that effective description is giving you so much revelation, which was completely unknown. You think about particle production by black hole, you think about cosmological particle production. What semi-classical gravity can do is basically opening you that, well, you have larger motivation to do quantum gravity. So of course, this is how physics will go on. Even you see after quantum mechanics, when you introduce, before we were introducing QFT, relativistic quantum mechanics came out. So people were trying hard that without invoking the concept of field, whether we can generalize the Schrodinger idea. The quantum mechanical treatment. Whether we can write down the quantum mechanical equations with just the relativistic effect without invoking field. So this is how actually we proceed, as I can understand.
Okay, we have another question, ma'am, from Saurabh Mandal. May the quantization of real scalar field, cosmic fluid in FLRW background, yield a loop evolution of the universe? More precisely, the microscopic loop evolution of the cosmic fluid can be considered.
Um, Shurab, I do not have direct idea about the concept you are trying to specify. The point is the quantization of a real scalar field, need the quantization of a real scalar field, cosmic fluid in FLRW background. See, FLRW background is still classical. Now, if you quantize the scalar field in the loop evolution of the universe, I really do not get this idea. I'm not aware of if anything is falling within
No
this
problem, no
construct.
problem. We have
Awesome.
another question from Abhijit Kumar. Uh,
Sure.
Ma'am, can we provide the study of black hole effect on particle with the help of tensor calculus like curve black hole solution?
Okay, but Card black hole solution is also done with the tensor calculation. I mean, why that is also a metric tensor. Gnu is used. Also, you can calculate Riemann curvature tensor. You see, Abhijit, the GR concept is based on tensor algebra. You cannot actually manifest a gravitational field with scalar and vector. How you know? There is a very nice discussions on the book by Gravitation book by Kip Thorne that if you see that when they try to do it with a scalar, it cannot justify the bending of light. It won't be able to justify the Mercury perihelion position. Also, if you take a vector field, they have the entire calculation that even if you try to design your gravitational field as a vector, let's say some x mu, not x not a good choice, let's say some capital G mu, like a vector of single rank, you will see that again, it will not be able to actually justify the observational effects. Observational effects like bending of light, black hole solution, Mercury perihelion positions, all such. So only the tensor G mu nu and that too symmetric is the potential candidate.
Okay,
And that is
MD,
absolutely will be there in case of car as well. Car black hole is not something else. It has just only one parameter extra. That is, it is basically a rotating black hole.
okay, MD explains is actually, ma'am, trying to tell that I meant why we assume that it is locally Euclidean, besides the fact that we want it approximation to Newton gravity locally. Is there really any other reason? This was actually his question. Einstein was originally inspired by equivalence principle, and acceleration in a curved space-time is equivalent to gravity in semi-flat or flat Euclidean space. Why, though we assume that it is Euclid? Then he writes, I meant why we assume that it is locally Euclidean, beside the fact that we want it to be the approximation to Newton gravity locally. Is there any other reason?
No, as long as I understand from your first comment, Einstein was actually motivated by the equivalence principle that I completely agree with you. But what equivalence principle tells us, it is not acceleration in curved space-time. It tells us that a uniformly accelerated body, it can produce a local uniform gravitational field. But please try and understand, it's a local gravitational effect, not global, because even it is that local that within that region you also do not have any tidal effect. So basically Einstein's equivalence principle motivation for to formulate GR was that a uniformly accelerated observer in flat space-time can be exactly equivalent to the local gravitational effect of a massive object, right? Like suppose you are falling with a uniform accelerations and you are standing on Earth. So the point is these two are locally equal, but Earth has a curvature. If you change the curvature a little bit, this description breaks down. So it's a very local descriptions where basically you just remember you are basically imagining a local flatness, and that is why you are able to bridge between these two. If you take the global picture, you will be never able to do that. Einstein was actually motivated from this that, okay, only one clue he got, perhaps, I mean, it is just all came with the storytelling, like that I can manifest gravity without formulating it as a force. I am equating it with a local accelerating object. So can I formulate it without invoking the concept of force and as a space-time curvature effect? So this was as long as my understanding came up. Now for the Einstein GR, under the weak gravity limit, you get the Newtonian gravity back. And that too up to the first order of perturbation theory. If you do the weak field approximation, then only you get the Newton's potential 2gm by r back, because then only Einstein's equation r mu nu minus half r g mu nu equals to kappa t mu nu can be written as a Poisson equation. Del 2 phi equals to 4 pi g rho, where rho is the mass density. Only under this approximations that I have a weak gravitational field limit. So this is
Oh,
what I can
right.
understand.
Okay, we got a quick questions coming up. Dave is asking, ma'am, when we consider Minkowski spacetime, then there is no notion of temperature. But after taking Bogoliubov transformation, we are having concept of temperature. How is it physically explained?
Okay, that's nice. Basically, Dave, you remember that the Bogoliubov transformation is a bridge between Rindler spacetime and Minkowski spacetime. Now, if you remember, as I said, that Rindler spacetime of that Rindler observer is such that it cannot access whole Minkowski spacetime. It is basically accessing only a patch. It is just like a right Rindler wedge of the entire Minkowski spacetime. It can access only a single wedge. So what happens is that, suppose if you remember, you start with the quantum mechanical idea that if you remember with a pure state, your phi was a pure state which was containing all the information and the initial information of the phi very nicely. But when you invoked the idea of Rindler observer, for the Rindler observer, beyond the t equals to x line, he will see that purity lost because he will never see any events beyond the t equals to x line. So for him, that pure state becomes a mixed state and hence thermality. So if you think it in a terms of thermal field theoretic language, a pure state is becoming a mixed state over here. It's a complete loss of information. You cannot retrieve its initial state. This is the same problem with the black hole, the loss of unity. Also, it can be addressed by some other means, but this is the same thing. So the pure state is becoming thermal due to the presence of the horizon over there. If you do not have the horizon, then we are cool. We do not have thermality. Vacuum is so nice vacuum. But Rindler one sees a horizon in the whole Minkowski space, and that is the problem. As it sees a horizon, anything falling behind the horizon is completely lost for him. And that is why he's seeing the real particle production, and hence particle production means radiation, and radiation leads to the thermality. That is
Okay.
how you can physically visualize it.
Right. So you got your answer. Another question coming up from
Yeah.
Abhijit Kumar. Ma'am, I was reading the string theory and I found that there that Bekenstein Hawking entropy formula suggested that every solution coincides with surface area. So GTR focuses on energy density.
Oh, yes, Abhijit, definitely. If you remember the right-hand side of the Einstein equation, it is basically a T mu nu. If you take the zeroth component of the T mu nu, that is T00, it is basically the energy density. That is basically the rho. If you take T0I, that is like a pressure density, right? If you, I mean Ti0, T0I is the energy flux. Again, Tij is the pressure. Everything, all these parameter T00 plus Tii plus Tij plus T0I plus Ti0 gives you the source in GR. And that is why your space-time is curved.
Okay. Devi is asking, is then temperature a relative concept?
Through that, bingo, you are there. Absolutely. Temperature is a relative concept. It's an observer-dependent phenomena. In flat space-time, at least so. And now in the curved space-time, we will see that it is an inherent characteristics of the curved space-time. This is still an observer-dependent phenomena. And you can tell me that, ma'am, it is a relative phenomena. Yes. In curved space-time, this is directly will come from the space-time itself. We need not to do anything else. Horizon is the culprit, Dave. Trust me. This is doing the trick.
Okay. So ma'am, are we left few of the slides? We will,
Yeah, I think yes, that is the Hawking radiation. I'm straight away going to the Hawking radiation
yeah,
part. So
please,
here also,
please.
Yes. So in case of the Hawking radiation, as again the Rindler transformation part, which one participant addressed, I have actually derived here that how a near horizon geometry look like a Rindler in 1+1 dimension. So if you see this ds squared 2, then it is basically like a Rindler metric. This is the Rindler metric. And this is the near horizon geometry of a Schwarzschild black hole. So it was a direct motivation that how we can actually anticipate that Rindler, as Rindler is showing some sort of particle radiation, why not black hole Hawking? A black hole will also show some particle radiation. So if I just quickly go to the black hole radiation, then here we can start, see, schematically, this is now, I hope it will be a bit understandable that near a black hole region, if I take the virtual, if I just bring any scalar field near the black hole horizon, and you know that the vacuum state of a scalar field, you have vacuum fluctuation. Now, in case of the vacuum fluctuation, it is constantly a particle-antiparticle pair production. Now, particle-antiparticle pair production happening in the vicinity of the black hole, the straightforward generalizations tells us that if in certain circumstance, one partner particle goes inside the event horizon of the black hole, and the other particle goes outside, what would happen? Let's say one particle falls within the black hole, it will never be able to come out. Continuous vacuum fluctuation was happening. Nothing was the problem. But you have a horizon over there. Suppose a partner particle will fall into the black hole and it will be never be come up, will be able to come up. So what happens? They will never be reunite again and annihilate. So it becomes, and then the one which is outside of the black hole horizon, it will straight away go to the eyes of the asymptotic observer, and he will see that, okay, there was a scalar field vacuum state, but suddenly I saw a particle came up because the partner particle couldn't participate in the annihilation. Now this partner particle, when it is entering into the black hole, as I already told you, that the notion of T and R, the space-like and the time-like things get flipped inside the event horizon. So the energy, it can be shown very nicely that the energy of that particle can be negative inside the black hole because the time-like symmetry becomes space-like, and it can be shown that its energy become negative within the event horizon. So as we are the asymptotic observer, I'm not obliged to, let's say, detect that negative energy particle because I cannot detect anything which fell into the R equals to twice m. I can only see that the positive energy particle came out. A negative energy one cannot come out because it's an unphysical particle for an inertial observer sitting somewhere at the infinity. So this is how black hole particle production takes place. But the main challenge is, you can straight away ask me, for a general relativity, you do not have guaranteed Lorentz symmetry. You do not have time translational symmetry intact. In general relativity, it's a curved space-time. It's a, let's say my background is curved. You do not have time translational symmetry. If you change your time parameter from t to t plus delta t, there is no guarantee that, like Schwarzschild, like a good behaving metric, it will also follow the time translation. So how to define vacuum state? How to define a positive energy state of the particle? Now, why am I saying this? It's a simple calculation. You just operate del t with a plane wave solution, psi xt. It brings down a capital E as a prefactor, and that capital E is greater than 0. This is how you associate a positive energy particle with a wave. But if you are not entitled to say that del t is my killing vector, then how can you do that? So in curved space-time, it is very difficult to define a positive energy and negative energy solution, and hence the vacuum state.
Dave is asking, can I get those slides for gaining the knowledge?
Of course, my pleasure, Dave. Be my guest. So the point is you cannot define this E greater than zero for a generic curve spacetime. And that is why in curve spacetime, we define at least the Hawking derivation was done that let's say initially the observer who is, let's say my eyes is the detector. So I'm sitting in some asymptotic region and there I can define my field theory. So that is how I made a schematic slide. I did this entirely elaborately that how we do it, but I'm not going into the detail of this. Let's say the last schematic diagram of this. In this case of black hole, asymptotic observer, let's say Bob, for him the vacuum state is Bolware vacuum because he has time translation symmetry with respect to the small t, the Schwarzschild time coordinate. Alice, who is like a stationary observer around the black hole, she has the time translational symmetry with respect to the Kruskal-Zecker time coordinate, capital T. You can define a Kruskal-Zecker vacuum associated with Alice and a Bolware vacuum associated with Bob. Now, if you calculate the number operator using the same Bogoliubov treatment, that Bob's number operator, but evaluated on the Alice vacuum, that is Kruskal-Zecker 0K, you get the particle potential. So the point is here, this I took the example of eternal black hole, but Hawking did it for a dynamically imploding object. At first, a star is getting imploded. It is basically getting crushed due to its own gravity when all degeneracy pressure and all everything exhausted. Star is becoming a black hole. Now, when the event horizon forms, he also did the same treatment. He defined the vacuum state for an asymptotic past where he made it like a flat space-time, and asymptotic future where the detector is in still flat space-time. And both of these vacuum states are different.
Okay,
And then he
just
performed Bogoliubov and got the number operator. Yes, please,
one
Shona.
question is that, ma'am, why is Hawking radiation, I mean to say, considered to be so important? I mean to say, why it is a unique thing? Is that we have never thought this earlier, or why?
Yes, basically in classical general relativity, a black hole cannot radiate anything, Shona. You cannot even associate temperature with the black hole. So if you see, someone asked about the Carr black hole. In Carr black hole, there is a process called Penrose process. So in Penrose process it is a classical process by which you can formulate black hole thermodynamics, but people were absolutely with no clue that okay, I'm able to write down something that I can extract energy from the black hole through the Penrose process. And I'm also able to write down some of the close equation like thermodynamics, but I'm not able to associate any temperature. From the Penrose process, when we write down black hole thermodynamics, you can write down that the black hole entropy is proportional to the area of the event horizon. But you cannot match the dimension. Entropy is dimensionless, area is dimensionless square. So many prefactors were missing. When later this quantization came up, when you bring in the quantum field theory in the black hole space-time, the entire Hawking entropy, the Bekenstein Hawking entropy told you that it is not only a area. There you have units like h bar, capital G, C, all sitting over there who give birth to a Planck square length, Planck length square, which can cancel the area dimension. So basically, the quantization of H bar was so important that it was never has been, I mean, it cannot be revealed without the quantization of the field over there.
Okay. MD Explains is telling, thank you for spreading knowledge for all humanity. I am probably 7,000 kilometers away from you, ma'am. And then he
My pleasure.
asks this question: do you think Bernard Schutz's book is good for a starter of general relativity?
Sure. Basically, that's a very good book, but I suggest everyone one review article by Matthias Bloch. It's a 900-page review article. That is my favorite.
Okay. Oh, he is from Germany. He is telling that I live in Germany, but I am originally from Middle East. Okay.
Okay, great, great. Welcome, welcome to this podcast.
Okay. One question coming up from Abhijit Kumar. Ma'am,
Yeah.
Friedman-Robertson Walker metric and its solution, different shape of universe. So if E is greater than 0, can also decide the shape of a black hole, means black hole shape always changing. Then he asked this question. I think this is not a question. It is not yet. Uh,
See, Abhijit, Friedman-Robertson worker metric is basically, if you see, that's a time dependent solution of Einstein equation. And if you see the TMU structure of it is excellent. It is basically time dependent energy density, time dependent pressure density. So that gives the Einstein solution as Friedman-Robertson worker metric.
okay.
It is not
Why?
static. It is not static, or it is not like our black hole, or neither is no star. Yes,
Okay.
please ask.
White Lotus is telling, yes, it is amazing. How much information can we get for free? Internet is made to discuss such topics. Okay.
Thank you.
And okay, one question coming up, two questions. Shall we take it once we complete this few slides, ma'am?
No,
Or we
I do
can.
not have any other slides. I'm done with the Hawking radiation part. If people are interested about the more mathematical structure, I can go along. Whatever is
Okay.
your choice.
Okay. There is one question coming up from is telling that string theory reach a dead end, or at least we need 1000 years to prove or disprove it, although there is no sense of proving a theory in science. Okay.
So,
And
is it a comment or a question? I mean, all these
I
I
think it
found
is
as
a
comment.
question, it is a comment. Yeah.
Okay,
Okay.
so
Raghav.
if you need any comment from my side, then I would request you very humbly, do not make such comments, because if you remember, the Einstein gravitational wave is discovered after the 100 years of its formulation. So the observational science took 100 years to compete with the pace of mind of Einstein. So if I'm making such statement that string theory is dead end or so, you never know what is going to happen in upcoming 50 years, 60 years, or 100 years, 1,000 years. So we, as a physicist, we go by facts. We only go by facts. If we see that it is not violating my known Newton equations, my extraordinarily brilliant observational science like standard model of particle physics, standard model of cosmology, Planck data, LHC data, and all, then we are okay with it. String theory is neither violating anything. It's not violating anything. It's the most elegant design of the universe. Maybe it has incompatibility with the observation, so we cannot make this generic statement.
Absolutely. Okay, Dr. Madhukrishna is telling absolutely an effortless lecture by Dr. Ashmita. Thank you, Dr. Madhukrishna. Thank you very much. Okay,
Thank you.
Raghav Manchanda has got a question. Ma'am, what is Penrose conformal cyclic theory?
Raghav, I don't know about the conformal cyclic theory, but actually Penrose transformation or the Penrose diagram, whatever I shown you, you're very right. This is actually, it is called the conformal transformation. If you see, the Penrose transformation is a conformal transformation of the theory. And that is why it is not changing any sort of basic physics underlying over there. It is keeping intact everything. It is just squeezing your space-time from some infinity to the finite region. So that is how I can say that it's a Penrose conformal transformation.
Okay, we have another question from Robert too. Could it be theoretically possible for the Unruh effect to create enough drag force to stop or deflect the accelerating observer?
I think, Roberto, you are talking about the back reaction of the produced particle, if I'm not wrong. Could it be theoretically possible for the Unruh effect to create enough drag force? So we are seeing particle production, and if you are talking about the particle back reacted on the accelerating observer, so theoretically, if I take into uh, I don't think so that it can deflect the itself the accelerating observer, because you know what happens in case of Unruh effect when we design it in terms of Unruh David detector just to manifest it observationally more perfectly. You actually we always do what you know that the Unruh David detector is. We always say that it is accelerating. The supply for the acceleration is basically coming from an external energy source, coming from some external engine or pump, let's say. So basically, it is not something I haven't I have thought about. If you're talking about the back reaction of the produced particle, I'll think about it. But if not, then it is not possible to actually deflect from its trajectory. It's a uniformly accelerating detector by design. So I don't think it is possible in that way, but I'll think about this back reaction point. That I'll definitely think. Thank you for
Okay.
asking.
Yeah, I
I'm
think
noting
that
everything.
those who have further questions, you can email me, or I will put up the email ID of Dr. Ashmita in the description box.
Definitely.
And also, I will
Definitely.
put up all the lecture notes, sorry, the scholarly notes, what Professor Ashmita has done in the description box, so that after that, those who are now visiting and later will visit can, look in those notes. Quickly,
Sure.
one more question which is coming up from Abhijit Kumar. Why time behave differently in quantum mechanics and general relativity?
Ha. So, Abhijit, it is very nice question, but to my understanding, why time behave differently in quantum mechanics? Because if you see in quantum mechanics, it is always like it is basically not a relativistic theory at all, where time we have treated with the same weightage as the space coordinate. So time differently behaves in quantum mechanics and differently behave in GR, because in general relativity it is absolutely the Lorentz vector of the space time which we treat relativistically under the same umbrella with the spatial vector. So even other than that, within the horizon, as I said, that the time-like killing vector is becoming space-like. This is the very profound idea. So as for Penrose process, so as for Hawking radiation, because the time-like killing vector change its notion to space-like. This flipping is giving me the negative energy particle within the black hole event horizon. As I'm not obliged to probe event horizon, that is why I'm safe. I'm not saying that, okay, the universe I can visualize, there everything I have with the positive energy. So within the event horizon, you do whatever you want. So the point is this liberty of having a negative energy within R less than twice n is absolutely different from the quantum mechanics to GR. And it is happening due to the relativistic formulation, due to the diffeomorphism invariance of GR, and many other presence of horizon, of course.
Okay. White Lotus has got a generic question. He's asking, ma'am, where can we find cosmology research in India?
Okay, so White Lotus, it depends cosmology observational or cosmology theory. So for cosmology theory, of course, you can have many institutes like all our National Institute of Technology, IITs, NITs, ISERs. Uh, Also, the many private universities are nowadays coming up with their, I mean, excellent research setup and uh, all the like facilities, at least that what I would suggest, that even central universities. So see, for the theoretical research, if you are want to do PhD, you have to just search for the web pages of all these kind of national institutes, irrespective of private or government or public, whatever. Just see the web pages and see that if you want to do theoretical cosmology, whose profile is resembling with your ideas, and if you want to do observations, I would not say there are much options, but Ayuka is definitely could be a good choice. RRI could be a good choice. RRI Bangalore could be a good choice. IIA Bangalore, Indian Institute of Astrophysics, could be a good choice. So these are at least offhand I'm getting at this stage in my mind. And also, of course, LIGO India is coming up. Let us hope for the best that it will give us an excellent platform to explore more about cosmology and astrophysics. Definitely, yeah.
Yeah, absolutely. We should be hopeful. One question coming up from Jason. We are led to believe that the speed of gravity is the same as light. If the escape velocity of a black hole is greater than light, how are we allegedly receiving any gravitational waves?
Yeah, yeah, the graviton speed is exactly equal to the photon, that I agree. If the escape velocity of a black hole, escape velocity of a black hole is greater than light, I don't understand this line. If the escape velocity of a black hole is greater than light, I think, how are we receiving any gravitational waves? I don't understand. Can you just
Yeah,
emphasize if the escape
that one
velocity
was
of a black hole is greater than light means what? I mean,
yes.
are you talking
I,
about that graviton's velocity? I mean, graviton can escape the black hole space-time or black hole's gravitational effect. Are you talking about that?
I'm also, when I read the question, it also was not very very
Yeah.
clear to me. Okay,
Okay, so the
so
gravitational wave is basically purely a classical concept. At least from my knowledge, that only I can say that it is completely a classical perturbation by which gravity wave propagates in space. But of course, if quantum gravitational description is considered, then those is containing with the graviton as a quanta, and it is actually the same as the speed of light. So if you are asking that how graviton is propagating, so see, when the two black hole is getting merged, in case of gravitational wave, or the neutron star is merging, or the any massive gravitational object is merged, or they're colliding with each other, there will be enormous ripple or the distortion of the space-time curvature around their dynamics, around their motion, right? Before they're merging, I'm talking about when they're about to merge, it's a vigorous repel which the space-time produces. Those are the basically the gravitational wave which we are recording nowadays. And that is, if you quantize, it is like a graviton as a quanta. So it doesn't mean that black hole is emitting graviton. In this circumstance, your space-time curvature's quanta is graviton. And as space-time is distorted classically, you can think of quantum field theory that, okay, my gravitational field is disturbed around it. And if I now think about it, the creation annihilation operator, graviton quanta will also be disturbed by its wavelength, by its frequency, and it will be recorded in your detector.
yeah, Saranda Se has rightly told. Gravitational waves are not from black hole, but they're due to merging of two stellar black holes, not from inside. It creates ripple in space-time fabric. I think you
Thank
also
you.
agreed to that. Yeah,
Yeah, yeah,
absolutely.
thank you. Thank you so much.
So, do we have? Shall I put on the presentation? You have few more slides, or we are done?
No, no, no. It is done. It is done. I mean, these are the previous slides are just the mathematical manifestation of Hawking, which is not, I think, necessary now because we had a lot of discussions about this Bogoliubov transformations. I hope people can relate at least with the curve space-time analogy. I hope so. If not, I'm very much quick at replying to email. So
Yeah.
please feel free to put me email.
So I can put off the slides right of now. So very intense discussion coming to an end, almost 2 hours. 10 o'clock, we started at 8 o'clock. One of a very long discussion, especially after Dr. Madhu Krishna. This is becoming the second longest podcast. And most importantly, I'm so much thankful to you, Professor, and to all the subscribers, because it started with 38, constantly around 32 to 33 people. They are all online, still 29, 30, it is increasing, and they have watched these 2 hours of intensive mathematical and physical description. It's amazing. So MD
I'm glad.
explains,
I'm really glad.
telling that wonderful discussion. Thank you, Dr. Ashmita and Shaunak. So thank you, MD Explains from Germany, etc. coming up. So last minute, any suggestion, Professor, you would like to give to the students, or anything that in terms of building up the career, how you are going up. Abhijit is also now telling marvelous, this one not, yeah, marvelous explanation. So
My pleasure.
this is this
You're most
this is what.
welcome.
Yeah. So, any last minute thought that you would like to give? First, I would like to ask you, Professor, how did you enjoy it with so many questions bombarding? I think you enjoyed the
It's
session.
just like, I mean, excellent. I mean, I don't have any words to just express. I'll maybe after this, I'll just straight away talk to my mother and father, and I will just express to them only, perhaps that, and of course, my sister. I mean, they are the three building blocks of my life. So I would rather perhaps explain them in detail that how much I have enjoyed. I mean, exposing to this range of audience, it is like. Excellent, excellent. Thank you so much, Rona, for offering me this platform. I mean,
And
I would never
any
expect.
last minute advice that how we
Yeah.
can. Yeah.
So at least I mean, as I deal with theoretical physics, I don't. I mean, I just want to tell you that one of my favorite line or quotation from the Steven Weinberg, Sir Weinberg, is that as a theoretical high energy physicist, perhaps we cannot see the immediate effect or impact of our work, maybe not even within our lifetime. But don't worry, your contribution will be recorded in history. So basically, if we can go by that romanticism and hold on our patience, then even if you get the minimal facilities, even if you get very minimal infrastructure, but if you dedicatedly go on with the concept, with the understanding of physics, what you started with, and where you want to go, where the questions, asking questions, and everything. I'm pretty sure that, of course, your contributions will be recorded in history. And now, if I just come to the very technical point, I would argue that in this background of time, I will suggest you that please follow your passion to from your BSc to your MSc, or if it is fourth year BSc, then please crack national exams like NET, JEST, GATE, all the entrance examinations of our Indian Institute. If you want to go abroad, of course, you please crack their GRE. Of course, please crack their subject GRE, TOEFL, IELTS, whatever is needed. I mean, just don't take any I mean, just don't think of any shortcut by which you can actually you want to crack. Don't do that. I mean, it's not necessary. Even if, of course, I can, you all can. I mean, it is not a biggie. So you can just start with those. Just follow the methodical ways of cracking those entrance exams. Try harder. TI for entrance, CMI entrance, IMSC, ICS entrance. Just explore everything around you and focus on the fundamental physics mostly. The building blocks, like, of course, classical mechanics, of course, statistical mechanics, quantum mechanics, mathematical methods. These are the bread and butter of quantum field theory, GR, and everything. I didn't say anything which is not, I mean, which is actually not came up from those building blocks. So if you know these 4 to 5 building blocks, all these entrance exam will be very easier to you. I mean, that I can assure. And then just follow the steps of the very, do it very rigorously and meticulously, whatever you're doing, maybe experiment, maybe theory, do meticulously. Even if you're getting many minimal infrastructure, please go ahead. That is what I can say.
Yes, thank you. So, MD Express finite classical mechanics, statistical mechanics, quantum theory, electrodynamics, optics,
Sure.
thermodynamics, Lagrangian, and Hamiltonian. And I would
True,
like to
true, yeah.
summarize what Professor told, that number one, follow your passion, whatever be the little infrastructure, build on the basics and look everything around. The world will definitely follow you, and whatever the work you're doing will be recorded in history, and you come up with big names. Thank you very much, Professor Ashmita. It is 2 hours, 3 minutes, and I think that if we can continue for 2 more hours, people would still be
Yes,
listening.
I don't mind.
But yeah, we have constraints in time. Thank you, all the viewers of Physics for Students. You really, really made this podcast amazing. I have never seen so many people constantly waiting. And MD Explains says, Krishna save you, Ashmita. Goodbye.
Bye. Bye. Thank you so much,
Thank you.
Shona.
Thank you, Professor. Just stay online for 2 minutes. So thank you very
Sure.
much and stay tuned for Physics for Students with more videos on Lagrangian general relativity coming up. And in the next one, we are in talk with Professor Ashmita that how we can schedule the next great guest speaker for another very important and fruitful discussion on physics and mathematics. Thank you, good night, and thank you, Professor, for your wonderful, tireless effort for 2 hours engaging and enlightening
My
us with the greatest concepts of physics and mathematics. Thank you very much.